I would like to welcome everyone to the product release webinar for the newest version of the Tasking Safety Checker. My name is Roger Smith. I am responsible for technical marketing at Tasking and will be the speaker for today's webinar. During the next 30 minutes, I will provide an overview on the main features of the Tasking Safety Checker version 3.0. As a recognized leader in high quality, functionally safe, and security compliant embedded software development tools, Tasking allows you to create best-in-class code size and performance with compilers, debuggers, and real-time operating system support for industry-leading microprocessors and microcontrollers. Let's take a quick look at the Tasking portfolio. In addition to the VX toolset for ARM, Tasking offers toolsets for the RX TC2, TC3, and TC4 families from Infineon. The Tri-Core toolchains are ASPICE Level 2 compliant, conform to ISO 21434 cybersecurity standard, and are TÜV certified according to the ISO 26262 up to ASIL D. With the acquisition of iSystem announced earlier this year, Tasking now offers a full system solution as the blue box establishes the debug and trace connection to the target embedded processor, and WinIDEA provides a versatile and powerful embedded software IDE. The Tasking safety and security ecosystem includes the Tri-Core Inspector, which provides embedded system developers a method for identifying if any SIL 2, 3, or 4 toolset related issues are in their compiled output code. The recently released qualified C libraries for Tri-Core will develop as a safety element out of context using state-of-the-art algorithms resulting in reduced memory footprints, reduced execution times, high numerical accuracy, and about 200 functions qualified for ASIL D use. The remaining functions are qualified for lower ASIL or QM. The Tasking Performance Tools, Embedded Profiler, and Multi-Core Performance Tool provide fast and efficient access to flow tracing information to resolve stalls, cache misses, and provide guidance on how to reach an equally distributed core load in your multi-core system. Finally, Tasking offers RX-optimized LAPACK performance libraries to provide accurate solutions for your complex mathematical operations, and the Tasking Pin Mapper tool provides hardware configuration and RX port mapping for your PCB development. Today, I will be introducing the newly released Safety Checker static analysis tool that helps ensure freedom from interference is maintained in ECUs with software components having different ASIL levels. This webinar will be recorded and available on our website at the link shown below. In case any questions arise during the webinar, we invite you to use the Q&A function on your Zoom console. All questions will be answered at the completion of the webinar. To let me introduce myself again, my name is Roger Smith. I'm an electrical engineer with over 25 years of industry experience designing, implementing, and debugging automotive electronics. In my previous role, I spent 12 years as an application engineer supporting braking, electrical power steering, passive safety, and ADAS applications for a global leader in automotive semiconductors. As the technical marketing manager for Tasking, I support a wide range of multi-core embedded software development tools. Before we begin, I would like to wish our attendees a good morning, good afternoon, or good evening, depending on what part of the world you're tuning in from. Every time I present a new embedded software development topic, I try to come up with a unique and relevant introduction. No matter how creative I try to be, I always end up falling back on the lifeblood of our industry, safety. Automotive electronics has evolved into a network of interconnected ECUs performing advanced algorithms relying on multi-core microcontrollers, data sharing, multi-threaded operations, and high-speed communication. These advancements have led to the most basic functions having an automotive safety integrity level rating. Many of these new systems based on multi-core microcontrollers combine related features and functionalities into the same ECU to improve vehicle packing density, minimize power requirements, minimize cabling and vehicle weight, while improving fuel economy, battery range, and CO2 emissions. In today's use case, we'll be looking at electrical power steering and GNSS navigation. Our goal as embedded software engineers is to design systems that are numerically and logically accurate, operate in a timely and consistent manner, and are functionally safe. If we look at the wall, it is not safe and does not perform its objective of providing a solid barrier. The foundation is missing blocks and the wall is full of holes. Our embedded software system also has characteristics and constraints that it needs to satisfy in order to be considered safe. Our systems must operate repeatably, and they must start and finish on time. They must execute completely and accurately. Algorithms need correct data and accurate data both as input and output. And our safety algorithms cannot be blocked or interrupted, and they need to have peripherals available when needed. Most importantly, our systems will inevitably fail. The importance is that they fail safe, as to not harm people in the vehicle or people around the vehicle. Let's start our discussion with an automotive use case. In this example, two automotive systems are in close proximity to each other. Available microcontroller space exists in the EPS ECU for some in-vehicle infotainment functionality. If we look at our electrical power steering system, you'll see the main function is to control an electric motor to provide torque to aid steering when necessary. You can see the main failure mode here that we'll be looking at is inadvertent steering torque causing the vehicle to turn when it's not the driver intention. This is an ASIL-D level fault. If we look at our navigation system, its primary function is to provide navigation information, and it must also provide redundancy in the event of losing satellite data. This is an ASIL-A or QM type application. So if we look at a high-level overview of our two systems, we can see we have the electrical power steering system here, which is an ASIL-D system, and we have our GNSS system, which is an ASIL-A. The steering angle sensor outputs utilize system peripherals like the analog to digital converters, timers for PWM, or the SENT protocol in order to get information into the algorithm. In the event of an imminent accident that needs emergency steering assistance, it is paramount that required peripherals are available when needed to maintain steering system accuracy and timing requirements. We can see here in our example that after the data is inputted into our algorithm and it's verified for plausibility, that for the torque data, we're going to write that directly to the motor control algorithm. In the steering angle sensor data, we're going to write here to the TC39X memory here, so you can see an LMU RAM that we have our steering angle sensor data. The motor control algorithm can then read that variable and then go ahead and perform its objective of providing steer torque assist information or demand information. If we look up at our GNSS application, this system relies on line of sight from the vehicle to the satellite in order to maintain positional accuracy. What happens, however, if the vehicle enters a city with tall buildings and the line of sight is now blocked? If we look at the easy scenario where it does have line of sight, we have positional data that's available to the navigation system through its normal mechanisms. However, if line of sight is blocked, we must now enable a system called dead reckoning. Now, dead reckoning maintains its positional accuracy, without having access to the satellite data. This feature uses the inertial module unit sensor data to calculate an estimate of the vehicle location until line of sight can be restored. The algorithm will use the yaw rate sensor and the steering angle sensor data for driver intent to determine if the vehicle has turned or not, and it will use the wheel speed sensor data and accelerometers in the IMU to determine how far the vehicle has traveled. This will give us some basic positional accuracy with some tolerance until line of sight is restored. So you see here for this particular example, we need to read now this steering angle sensor data from the LMU RAM. The position data and steering angle sensor data will then go into our navigation algorithm, and then we will have our next navigation instruction available for the driver's use. Here you can see our potential issue. We have both an ASIL A and an ASIL D algorithm accessing the same variable. So why is partitioning important? Here we're going to look at the same use case in a slightly different manner. Here you can see we have our ASIL D electrical power steering application with its own segment of memory or block of memory here in LMU RAM, and we have our ASIL A function with its own local memory. So now remember that in the event of an emergency stair event, the ASIL D application, may block the ASIL A application. So if we look at the converse, however, the converse is not true. And so the infotainment system may read the EPS stair angle variable, but it must not write or block execution of the EPS system. What happens if a wild pointer occurs? You can see here that a wild pointer occurs and it actually enables the motor. And what this does is this enables, or this creates a ASIL D safety case violation where we have an inadvertent motor causing inadvertent motor torque, which is adversely affecting the driver. So as developers of safe embedded systems, we must maintain some ISO 26262 compliance. Now, in the previous example, in order to maintain this compliance, the designer has two choices. The first choice is he can design the infotainment system to be ASIL D, and this can be very costly. The alternative is that he can place his ASIL D software component in one partition and his ASIL A software component in a separate partition, and then guarantee spatial separation or freedom from interference. So what is freedom from interference? At a high level, a partition software component cannot be allowed to contaminate another partition software's code, input-output, or data storage areas. The following faults must be prevented or detected and mitigated to ensure freedom from interference. These include memory, timing, execution, and exchange of information. So now let's move on to the safety checker. So what is the safety checker? So the safety checker is a static analysis software development tool to help ensure that freedom from interference is maintained, and it helps to assist with the ISO 26262 ASIL certification. The safety checker also helps to ensure that safety coding guidelines and rules are used in your multi-core application. Now you can see here in the lower left-hand corner, we have a couple of junior engineers who are wondering, what actually does static analysis mean? It's a term that's used quite frequently. Static analysis is a method of computer debugging that is done by examining the code without executing the program. And you'll see that that's going to become very important in the next couple of slides. So how does the safety checker improve your development process? The first answer is it reduces your development time. So when you use a memory protection unit to guarantee spatial separation between safety and non-safety software components, we see a couple different options or points here that we must consider. The first thing here is that memory violations after the MPU is enabled will result in a trap. These traps are very time-consuming to debug and require additional software engineer resources. The safety checker, however, does provide a list of memory interferences, and these can therefore be resolved prior to enabling the MPU, which makes our overall development process more efficient. Furthermore, the safety checker can be used in continuous integration and continuous development environments, and this allows us to detect these MPU problems early and to prevent broken build jobs. One additional way to take advantage of the safety checker is that you can merge it into the verification step of your software. This again helps to prevent broken test runs, as MPU violations are usually found during integration or system tests. So let's take a look at an example here. So during development, we're going to go ahead and we're going to enable our memory protection unit, and unbeknownst to us, we have 10 MPU violations which are present in the software. Well, as we're attempting to run our software, these MPU violations are going to result in traps, and now we have to debug each one of these traps individually, one at a time. And you can see here that we've taken a guess here that each one of these debugging steps is going to take approximately 2 hours. because part of the process of doing this debugging is we have to modify the configuration, we have to generate our code, we have to compile our code, we have to go through the build process, we have to flash our ECU, and then we have to go ahead and debug. So you can see here with 10 of these so-called errors that we're looking at about 20 hours of time that is required. On the converse, if we look at using the new safety checker tool, the safety checker will give us a list or many of these interferences up front. And so we can, even though it takes a little bit longer to run the safety, to do a run of the safety checker, we're able to capture multiple issues at the same time and resolve these issues. So the overall time spent is reduced, making our process more efficient. Again, the key point here is that debugging a trap one by one is a time-consuming process, and it requires software developers. And don't forget, it also requires development equipment. Another benefit of the safety checker tool is it allows us to ensure freedom from interference without actually using a memory protection unit. So using the MPU can lead to some negative consequences during your development. First of all, the MPU context switches are runtime expensive, and they do negatively impact our execution time. Secondly, there's a limited number of MPU regions that are available on your microcontroller. This requires additional configuration delays in your overall system time. So with the safety checker, ECU integrators can now show that your software is disturbance-free with software components of different ASIL levels in the same partition without an MPU. So the safety checker is going to support in the memory domain, and the time domain is left up to your existing time monitoring functions. If we go ahead and if we look at another example here, you can see here that we're attempting to integrate a QM module into an ASIL B partition. You can see here we have a number of different steps or tasks that have to be executed. We have a periodic task, and that's going to require 4 context switches. We have 2 tasks which are being interrupted by an ISR, which are taking 8 context switches, and then 2 calls to the OS, which are taking another 4 context switches. If we look at a context switch taking about 3 microseconds, you can see here that the overall time to execute these tasks is about 48 microseconds. So if we can get away from using the MPU, we can see almost a 0.5% savings in our runtime. And this represents a tangible improvement in our runtime savings. Remember that safety applications have multiple tasks, and the interaction between these tasks can increase non-linearly. And so the safety checker can provide freedom from interference without a memory protection unit. If you are unfamiliar with a task switch or a context switch, I'd like to explain it here briefly. So you can see here that we have, so say we're executing task A, and we receive a software interrupt to switch to the OS. Well, we must execute a context switch before switching to the OS. So this involves, to stop executing of task A, we need to save all of the task A key data, like the program counter, the stack pointer, key registers, etc. Next, we need to restore all of the OS key data so that it can run properly when enabled. Now, the key point to remember here is that during the context switch time, no work is being done. So the time to save all of task A and to restore all of OS is just overhead or wasted time. Now, after the OS key data is restored, now we can begin executing the OS task. So now let's take a look at the safety checker and some of its main features. So if we look at products and services, one of the key points here is that with Safety Checker version 3.0, it does come with a plugin which does support a GUI, and this GUI does help to define safety classes, access rights, and to map files and functions to different safety classes. So it's a big time ease of use adder. We support now reading in AUTOSAR configuration files for versions 4.03 and version 4.4. And as previously mentioned, you can improve your development speed through the early detection of these MPU access violations. I've listed here in a number of additional features of the product, which you can review at a later time. If we look at our gain creators, we now offer a crawler, which kind of goes through your build process and it identifies files and functions to help ease the generation of your configuration file. And also now the safety checker can be integrated into build environments like Jenkins, and you can actually call it from Jenkins, and you can, view the results on the Jenkins server. And then it does offer also a number of pain relievers. Now in the report generation process, you have the options of choosing either HTML, XML, or PDF formats. And then you also can minimize the number of false failures because you have a chance to highlight in your code those key areas which can be problematic in terms of how they're working within your safety definition. So the key point here is that the safety checker allows you to detect when a lower level ASIL or QM function is attempting to execute, write, or read a higher level ASIL function. So how do you use the safety checker? So the safety checker can be used via the command line. And as mentioned previously, the new version offers a plugin that supports a new graphical user interface for ease of use. So the safety checker needs a safety access file, and then it will create an error file which reports all the freedom from interference violations. So I've taken a couple screen captures here of the tool, and you can see here's where we're defining our partition. So in this particular example, we've configured an ASIL A, B, C, and D partition, and then we've also, with the safety checker, you have the ability to create multiple partitions within that are within, like at an ASIL D safety level, and then you can still define the access rights between these different ASIL D subpartitions. If we look here, while we're creating our safety access table, you can see that we can define here the rules or the relations between these different partitions. So for example, here you can see the My Data partition has read-only rights for the OS application 0, but the OS application 1 here has both read and write privileges on the OS application 0. Another feature of the safety checker is that it allows us to map source files and functions to a particular required partition to just help break down your code and define it throughout your overall safety access requirements. We can't forget about memory. So you can see here, we can also assign requirements to our memory blocks. And so here we have a starting address. We have the size of that starting address, and then we can define whether it's an ASIL A, B, C, or D, etc. In order to make life a little bit easier, you do have the capability or the ability, to import a previously created safety access file to help with the creation of your new project's SAF file. Here I've actually run the safety checker to give you an idea of what the results look like. And so if we come down here to the errors, you can see here that we denote the C file for you, the line at which it occurred. And then we see that we have the QM main is attempting to write a ASIL D test function. And you can see here also that 5 different errors are shown. And so unlike the earlier situation where you're trying to debug a single trap at a time, here we can go now to the appropriate lines within our source, and then we can fix 5 of these errors all at the same time, which again reduces this build, compile, flash, debug step as described earlier. And here I just show a little bit more details here on what's involved or what can be included in the safety checker report. So here you can see where we specify the memory address, which safety class it belongs to, what the starting address size and safety class is, and whether that memory location was accessed. Here we can see that we have the main function is located in the tc2x_demo.c file, and it has a QM safety class rating. And then here we have the safety class access rights table. And here in this particular example, you can see that an ASIL C level partition has the ability to read, write, and call or execute a QM partition. And then down on the bottom, we do show some different details here on the call graphs in terms of what functions are calling, what other functions, and the information that's being passed, and the safety classes, etc. So in summary, automotive ECUs, as shown in our example, integrate multiple features with different safety requirements, all within the same device. And so the tasking safety checker is essential, to prevent errors in non-safety critical software components from introducing errors and failures in your safety critical software. So some of the characteristics to remember from the safety checker are that it does ensure freedom from interference with ASIL-aware static safety analysis. It does check for illegal function calls and memory accesses. It reduces your development time by detecting memory interferences prior to enabling the MPU. It does now offer a nice Eclipse GUI to ease the configuration process. MISRA C, CERT C, and SIL aware safety checks are included, and you do have the flexibility in generating reports in either the PDF, XML, or HTML format. So as kind of a general summary, Tasking offers a complete ecosystem of safety and security compliant development solutions for embedded multi-core software development. So I'd like to thank you very much for joining our webinar on the Tasking Safety Checker. If you're interested in additional information, please see the following contact information. And now we will move on to the Q&A session. So let me look through here and see what questions are available. So we have a couple questions here. Yes, this is a question that a very good question. So what licensing models are available for the safety checker? So Tasking offers a flexible licensing model, which is time-based license only for this particular product. A time-based license is one that has a fixed duration, say on an annual basis, for example. Floating site licenses can be purchased. No node lock licenses for this product will be offered. And build server licenses are also available, and they're offered for both, like a small and on a large scale. So for example, a small scale would be like a single project where you're working on an application to a tier 1 or OEM. And then like a larger project would be, you're working on several projects, you have many software variants, you require, multiple build machines, etc. If you do have a specific use case for your licensing model, again, here you can contact us at tasking.com/contact, and you can then get in direct with one of our sales account managers who can, talk through your specific license use case and figure out, the best way to solve, that particular issue or problem. Okay, here we have another question. So I have previously used Safety Checker version 2.0. So what explicitly or what's new in version 3.0? So some of the main things that are in version 3.0 is the Eclipse-based graphical user interface, which dramatically eases creating of the safety file or and setting up your project, before running the safety checker. It does allow you that AUTOSAR configuration file import capability. It does lead to less false positives, by, allowing you to test by marking within your IDE those code sensitive areas or code annotations. It does offer the code crawler, which will kind of, go through the process and identify your different calls, etc., to different functions, and identify some of these different functions and C files to help you to create this file. It does provide you the extended report generation, and also I would say probably the Jenkins and GitHub support, which allows you, for improved CI/CD environment development. Let's see here. Oh, this is a complicated question, but let me take my my best swing at it here. So I'm developing motor control software with Infineon TC387, and I'm being directed to use the Tasking compiler. How else can Tasking help me with my ASIL-D software development? So this is a multi-part answer here. So since you are using the TC387, you would be using the VX toolset for Tricore version 6.3 R1. That toolset is certified already by the TÜV Nord for ASIL-D software development. So you kind of, you check a box right there, right off the bat. I would recommend you to contact your tasking sales account manager and purchase a qualification kit for this tool set. So what the qualification kit will do for you is it will give you access to our issues portal, but more importantly, it will give you the safety manual. And the safety manual is going to show you which tool set options are qualified for ASIL-D usage, as well as provide you with some supporting documentation, which will help you to complete your safety case requirements. A couple more things that Tasking provides. Last month, we did a webinar where we introduced our qualified C library for TriCore. And so if your application is using any standard or, ISO C mathematical functions and you're using it in your motor control ASIL-D software development, you either have to qualify those QM functions yourself, or with purchasing the Tasking qualified C library, those math libraries are already qualified for ASIL-D usage, and so that will, again, ease your development process. And then probably the last two options I would say is you have the safety checker, which we just talked about here today, where that can help you to ensure your freedom from interference. And then we also offer the TriCore Inspector, which allows you to identify if there's any known issues with some safety concerns are present in your compiled source code. And then we also, with the issues portal access, we also give you some ways of either mitigating or how to resolve those issues, or you can then request a patch if the mitigation issues that we provide are not good enough. So I hope that answered that question. Does the safety checker also support the Infineon TC4X? Yes, it does. So the safety checker is not compiler or architecture specific. So it just, it's based on ISO-C, and it basically works off of the idea of the call graph, so the safety checker is able to, review or build a call graph, see what information is communicating or being passed back and forth to one another, and then with the safety access file, that's how it helps you to identify these MPU violations. So those are all the questions that I see. So I hope that today's webinar was helpful for you. If you have any questions that after the webinar, please don't hesitate to contact us, and we can put you in contact with one of our sales account managers or one of our the technical support members on our team, and then we can answer your questions. So with that, I wish you all a great day, and hopefully we'll talk to you soon. Thank you. Bye.